Hello and welcome back to the Oxford MAT Admissions Test live stream, or welcome for the first time if you're joining in with trigonometry for the first time. Great to have you with us. I think I've pressed all of the right buttons and I'm now live on YouTube, but you'll tell me if no, you won't. I'll have to wait to see if you tell me that I am live. Hello in chat to Ginger Biscuit. Let's put chat on screen. And fantastic to be here. We've had open days for the last couple of days, events over the weekend as well. So I've met so many people who tell me that they are already joining in with the MAT Admissions Test live stream. It's been fantastic to meet people out there in real life as well as on live streams like this one. Like Bill Ice, good. Yes, I've correctly pressed all the buttons. Fantastic. Good thing too. So open days are interesting because I never know whether these days we hand out these stickers that point people to this website. I never know if that's going to work and people are going to sign up, or if they're too busy still at the open day, which is still ongoing behind me. Let's see how that goes. Hello Mary as well. Good. Right. Okay. Let's find out how chat's doing today. I always like to ask, if you're new here, how they're doing. If you want to join in with the voting, later on we're going to vote for which question we should do from the revision questions and then from TMUA questions. If you want to join in with that, there is a Slido. It's got event code MATLIVE, or you can click a link in the YouTube description or at the homepage. The homepage is pretty easy to find. Hopefully if you search for MATLIVE, Matt Live, it turns up there as well. It's maybe how you found this live stream in the first place. And possibly you've just come from an open day and you're wearing a sticker that has the URL on it, but it is also on the screen as well there. Right, fantastic. Chat's having an amazing day so far. Look at that. What a fantastic day they're having. That's brilliant. The way this works, if you're new, is that there is a worksheet over on the Matt Live page, which has been live for about a week. Oh, hang on, let me just... I'm going to show you the worksheet. Let me just log out of the website. Yes, please. MATLIVE. There is a worksheet which has been live for a week. So here's the website at the bottom here. And down here, there's a table of what we're up to. And the trigonometry worksheet here takes you to a link where you can print a PDF if you like. The thing that I'm scrolling at the top is the PDF. But you can also just scroll down and read it online. If you're on mobile or something, this one resizes nicely, you see. This has got revision notes about triangles that we'll cover, and there's some revision questions. I also pushed the solutions. So you could currently be trying next week's questions on logarithms and solutions. You can get a week ahead of me. If you like, you don't have to watch the streams at all. But part of the fun is that we run these live streams on YouTube so that people can drop in and tell us how the day's going. 85% brilliant, 6% terrible, 94% brilliant, 4%, 6%, 5% terrible. So I'm always looking out for people who are having a terrible day, because I sort of think maybe doing some maths and knocking the maths out of the park might be the thing that you need to have a terrible day, to have a brilliant day. Oh dear, open day is going to bite me, isn't it? Sebastian in chat is on the way home on the tube. We've got chat going as well behind the scenes. And Aperigon. No, Aperigon. Aperigon. Is that a word that I know? There's a thing going on in chat where you can set your username to be your name if you like. I won't know whether it is your name or not. Or you can put the name of a mathematician if you prefer. Or if you've always wanted to try out a different name, you can give it a go here. I'm not going to go. Brilliant. Right, okay, people are turning up. There we go, okay. Question while we're getting ready, while we're getting people together. Here's a quadratic equation question. So the way this question works, just as a starter for something to try, suppose you know that the constants a and b are positive, and there is another question in here there's another constant in here that is alpha, with just some angle. And the question says, find conditions on a, b, and alpha such that this quadratic has exactly two positive solutions x. And if you like, I would like it to be the case that each of these conditions you find should be necessary, and all of them together should be sufficient. So that between your conditions, various facts that you will write down about A and B and alpha, putting it all together will give you precisely an understanding of when this thing has exactly two positive solutions, x. So not just two solutions, but two positive solutions. Although that's already giving away part of the answer. It's a polygon with infinitely many sides. Thank you so much, Taz. I knew it looks like a word. Thank you. Pranavi SK in chat says, should I focus on the prior worksheets next week or just work on the upcoming ones? Didn't do previous ones. It's your choice. If you're watching live, you could join in with this one if you like, but you're also welcome to pause the video, try the questions, get ahead of me while I'm paused, frozen in time, get ahead of me, and then join in afterwards. In general, I think it's slightly more fun if you've looked at the worksheet beforehand, which is why I'm publishing it a week before, but it's supposed to work either way. Right, other people around you are going to be voting on things, which is going to happen. Okay, good. And Callie in chat, let's shout out to Callie quickly. Thank you for the voting, we're having a lovely day. Callie in chat is a current student who is moderating chat and helping answer questions as well. There are going to be future worksheets as well, points out Callie, so you could wait for one where you want a particular topic. Which is good. If you can see logarithms coming and you know that you haven't done logarithms in school, then that might be a fun one to see. Right, it's Dexter, the GCSE boy. What a username. Dexter, I feel like that's I feel like you could just put Dexter. But you put a handy reminder for me. Sorry, that's really tickled me. Oh dear. Okay, right. And SB as well says hi. Good, right. What do we think of this quadratic, chat? It's obviously inspired by something in the notes, if you want to see it. I'm going to do a sort of split screen thing here. Let's just hide chat for a second. The split screen effect is I can have my notes at the top. So revision, facts about trigonometry, facts about triangles. At the top, the things that you need to know for TMUA. Several things on there, including knowing about sine squared plus cos squared is 1, everyone. This week, unusually, we're including an extra fact about congruent triangles. Last week we had some bonus facts from geometry, so it's a bit like that. So second time round, I'm doing this where I include a little bit from this thing called section M5. Do you see that section symbol? There are different sections of the TMUA specification. Most of it's A-level maths, a little bit of GCSE. I have, on 2 occasions, picked out some of the GCSE maths because I think you might need to revise it depending on what you remember from there. Okay. Revision notes down here. So we got pictures of triangles and things like that. This year, the new thing for me is that TMUA questions are written in either degrees or radians. Could be 1 or the 2, so I have got these 2 tables of special values for you to look at. The only difference, of course, is the labels along the top, because degrees and radians are just different ways of labelling the same angles. And there's some formulas in here you need to know about triangles. These are some of the longest sort of revision notes that we've got, partly because I have added in, looking at that TMUA specification and the way it stresses about, it emphasises congruent triangles, I've added in all of the rules for congruence, which for some people is GCSE maths, but that might have been a while ago. And I have a long bullet point about the ambiguous case, during which, if I've done this correctly, appears I've done it right, exactly this quadratic, but for C instead of X. So I would like us to think about that quadratic now, if that's right. Good. Okay, I'm going to scroll this back up to the top. I've done that wrong. Right. I think I've done it in a way where you can't tell how much I've just messed up. Which is sort of worse, right? At least if it does a technical error that you can see, then you know that something's going wrong. Whereas here, it says, oh dear. Oh dear. Right. Okay. That's just upset me. Oh, what am I doing? Right, we're going to quadratic. Chat, you've got any opinions? Chat says, hi Kelly, how's your day been? Which, fair enough. Good to see Kelly. Has Kelly had a nice day? Let's check this comment. Kelly says, feeling pretty good. Summer vacation just started. Lovely, good. It's such a long summer, Oxford. Really good. Any thoughts about my quadratic? The conditions were just on screen, I suppose, because they're an ambiguous case, but I would like to talk about where that comes from, because that bit of the revision notes is, I think, important and already quite long. So I didn't want to type up all of the kind of step-by-step, because I thought it would be a bit scary to have too much. Yeah. We should think about the discriminant, should we? Shouldn't we? Yes, good. Chat can be on screen for this bit. We should think about the discriminant. Ooh, A over B greater than cos alpha? Question mark, though, which I like. I've been explaining interviews to people a lot today at the open day. So I'm in interview mode, is like, aha, there's a question mark, so I can ask, why do you say that? Where's that come from? And we can jump in to find out what's going on. Right, okay. So to have 2 positive solutions, it is necessary to have 2 solutions. If you don't have two solutions, then you definitely don't have two positive solutions. You don't have two even solutions. You don't have two solutions between 1 and 3. If you don't have two solutions at all, then you won't have two solutions. So necessary condition. Let's write that down onto here. Oh, shall I go full? Yeah, let's go full. I can do both. Look at this. Okay. So necessary to have ... two solutions. Journey of 1,000 miles starts with a single step. The journey to two positive solutions starts with, well, having two solutions for which you need the discriminant, which is 2b cos alpha squared minus, I'm going very slow because chat is right here. Oh my goodness, there you are. Minus 4 times, you know the discriminant, b squared minus a squared to be greater than 0. Oh, I mean strictly greater than 0. If I come down here. No, it's terrible. We're turning off chat. Euclid says you stole from my book, which is really like leaning into the mathematicians in chat thing that we're doing, apparently. Yes. Username James should love categories. So dispute. It looks as if A is the side of a triangle, B is the hypotenuse, and b squared minus a squared is the other side. Great idea. Squared, yes, and then b cos alpha is another other side. Yes, I get right. There's a lot of triangle stuff going on, isn't there? Both of these involve 4, so this actually simplifies this discriminant. There's a b squared cos squared alpha here, minus a b squared plus an a squared, which gives us, there was a question mark on it earlier, but ages ago there was something with a question mark. Something like, what am I going to do? I'm going to keep the a squared on the left, and I want it to be larger than, I think this is b squared sine squared alpha, you know. That's 2 steps for the price of 1, I suppose, but I've moved the 1 minus cos squared over here and written sine squared because that's faster. Which I think, because everything is positive, because a and b are positive, this is the same thing, and sine theta, I suppose. No, what do I want? I was gonna square root everything, but I should be careful, shouldn't I? I should be careful. I've left this slightly more open than I imagined. Fun times, good, okay. Oh no, what am I gonna do? I was supposed to tell you that alpha was between 0 and 180 degrees, and I haven't told you that. I've accidentally got a second half. Yes, look at those 3 question marks from John Math. Oh, no, you can't see them. Look at those 3 question marks from John Math. There was a thing a few years ago on this Office Hours YouTube live stream, whatever we're calling it, where people we had a quite developed system of the more question marks, the more unsure you were. We've got some nuance, right, that people would have. So 3 is quite a few, but not as many as 4. Yes, I think I'm stressed because I was going to write down a greater than b sine alpha, but that's only actually valid if sine alpha is positive. So what am I going to write instead? I'm going to write a true fact, aren't I? So a is positive. We're going to need a to be larger than b times the absolute value of sine alpha. Good revision for absolute sine values and how to square roots work. So we need a to be larger than b pod sine alpha. Now, having done that properly and put the absolute value signs in to say that it's going to be larger than the absolute value sine alpha, so that if sine alpha is negative, that's actually, you've got to have a large value of a. Having done that properly, I'm now going to cheekily go back and change the question, because there obviously should have been an alpha in here. Whoop, let's fix this. Whoop. Right, use my magic to modify the question on the spot. I should credit Euclid? Oh, come on, because it's triangles, right? Did you have cosine Euclid? You know, cosine and sine? I don't think you did. Hello, Count Monte Cristo. Good. Okay. Still got sidetracked though. If alpha is between 0 and 180 degrees, secretly there's a triangle going on, so alpha is between 0 and 180 degrees, so I don't really need these because sine alpha is definitely positive. Okay, what else have we got? So it's some discriminant fact. So the modulus down here is because before I put in this comment up here, before I put in this comment about alpha being in a particular range, I got very stressed about the case where if sine alpha is negative, which it really could be, then the rule is not, then it's not a greater than b sine alpha. Is it? Because yes, because b sine alpha would be negative, and a could be, because that includes numbers like very, very small, or even negative numbers, things that are close to 0 over here, that are technically larger than this negative quantity, but which have a very small square. Taking square roots of inequalities is really hard, and something you should be really careful with. That includes things like 0 greater than 1 times minus 0.5, to pick some random examples, which then, really we need this thing. This is the truth of what the discriminant really is, and it's not the case that 0 squared is bigger than negative 1/2 squared. You see, there's this kind of difference about it. Having a large square is about being far away from 0 on the number line. So this rule here says that a should be further from 0 than b sine alpha is. So the correct thing to write down in general when you have x squared greater than y squared, the correct way to simplify that is to say that the modulus of x is greater than the modulus of y. The distance from 0 is larger. Now in this case we know that a is a positive number, so I don't have to write the modulus absolute value signs on that one, and I know that b is a positive number, so I can bring it out. But technically this is what you're supposed to do because of this case, right? I feel like we've seen some inequalities. Was it on the algebra sheet where we were told about inequalities and the dangers of multiplying and squaring and square rooting? So I can't just flip the inequality sign because I'm worried about sine alpha being negative, and I'm worried about cases where sine alpha is positive. I don't know which it is. That somehow, if they're just numbers, a, b, and sine alpha, then I don't know which case I'm in. And I sort of want to write down a true factor that's kind of true in either case, which is what this modulus sign's capture, right? If sine alpha is positive, then fine. If sine alpha is negative, then put a minus sign on it. But it's a conditional thing, right? If it were just always putting a minus sign on, then yeah, flip the inequality, do some like, it's a negative number, don't stress. But because it's sort of sometimes positive, sometimes negative, and that matters, pretty tricky. Ooh. Hey, Charlotte. Good. Right. Okay. So that's one condition. That's necessary. What else do we need? So we've got 2 solutions if we do this. But the question is asking about 2 positive solutions. And I think we'll work with my modified question where we've got this range for alpha so that we can stop worrying about one side. Well, I think that was helpful. A helpful thing for us to worry about. The inequalities work with squares that you would like to get rid of. What else can we say? So necessary things. I'd like to say stuff about the coefficients of this quadratic, if we can. So what can you tell me then? If this quadratic has got solutions that both happen to be positive, that's got to mean something about these coefficients, I suppose. Let's put them in brackets. These things in brackets in here could probably tell me something, I think. Let's find out. Good. Yes, okay. Here it comes. There's a cube in the moderation journal. Let's go. Good. Now I've got to think about what happens. I'm glad this happened. It surprised me because I forgot to put my range in, but on the other hand, it means we had a nice chat. Gosh, this is good fun. Anyway, does b squared minus a squared have to be positive? Yes, true. Yes, there's some conditions that do this in chat where people are thinking about the quadratic formula and thinking about the terms that you get in the quadratic formula. And there's some, everyone's sort of rearranging it together, right? Nice. So like minus b plus or minus. And I think that's going to lead you to, because the discriminant involves b squared, I think that's going to lead you to something involving the constant c. And Daniel at the top there has got this idea about cos alpha. Eddie Sparrow explains that's the sum of the roots. There's this minus sign here, which means that this thing in brackets really is the sum of the roots. So necessary to have positive. Oh, how do you spell? There we go. Positive sum and product. So I don't know if you know this, but if you have something like x squared minus 5x plus 6, then the kind of factored form, if you like, this number at the end is the product of those roots, and this number in the middle is, think about minus signs really carefully, this number here is the sum of these roots. So I should write 2 and 3 in here, because they multiply to 6 and they sum to 5. That's probably not what's going on here, but sure. Positive sum and product means b squared here. B squared minus a squared should be positive, and 2b cos alpha should be positive as well. Now this is quite good. We get a couple of conditions here. We know b is positive, so we need cos alpha to be positive. Yeah. Yes, so then we want b to be greater than a. We're safe here, really. So here's another example where I have some squares, and really I should write the absolute value of b is greater than the absolute value of a. But I did remember to tell you that the numbers were positive numbers, so we don't need to worry about that here. We don't need to write our absolute signs. You can if you like, but everything's fine because positive. Okay. Yeah, so alpha should probably not be 90 degrees. Alpha should probably be something such that cos alpha is positive. This bit's positive because b is positive and 2 is positive. Welcome to the Oxford MAT Submissions Test live stream. The number 2 is positive. So we need cos alpha positive. Why is the product positive? Well, if the two solutions are positive, then multiplying together two positive numbers gives you a positive number. So this over here, which is secretly the product of those two solutions, would have to be positive. So here's actually the cos alpha thing, given the range, which I should have given you at the start, says that actually you need alpha between 0 and 90 degrees. Now, these are kind of the same thing in this range, which I really should have given you. I'm going to blame the open day. Okay, so we've got a bunch of necessary conditions. You need to have two roots. That's the thing on the right. And you need, if they're positive, if they're both positive, then their sum will be positive, their product will be positive, loads of things will be positive. So you need lots and lots of things. Often in maths, if you start if, then you can follow that with quite a lot of thens. So if then, if there are two positive solutions, then you can add them, get a positive number. You can multiply and get a positive number. You could take their ratio and get a positive number, but that doesn't seem to be related to this question. The interesting thing, I think, is that between them, these three conditions, let's keep the absolute value in. Although if I'm in this, well, I'm going to guess. For these three conditions together are also sufficient. If you have all of them, then your quadratic at the top has exactly two positive solutions. How do I know that? This is the other way around, right? This is, instead of saying if it has two positive solutions, then yeah, it's easy, just add them, you get a positive number. And the other way round, the thing is that here, if I know that there are two solutions, then I can start to think about what I can infer from their product and their sum. I still know that these are the product and the sum. I don't know the roots yet. And going the other direction, a positive product means that they have the same sign as each other, either both positive or both negative. So you really need all three of these to have a kind of sufficient condition together, all three together, because I need to look at the sum as well. This coefficient here. Okay. Yeah, so the question now says that alpha is between 0 and 180 degrees, but that is a change that I made. Yeah, so sorry, so alpha is between 0 and 90, so we no longer need the absolute value signs, says Mumbo Jumbo in chat. Oh, sorry. Yes, I only really included it for the chat. Maybe I should include this thing up here, and then I don't need to worry about this because positive. Same colour over here. Lovely, good. Okay, so these three things together, angle is acute, and A is less than B, but A is larger than B sine alpha. Those are the conditions for you to be in something called the ambiguous case of the sine rule. Now there's a picture of what that means in the notes, so we're going to have a quick look at the notes underneath here. So all the way down back through the notes. Why did I scroll back up again? Down here there's a picture where that triangle on the left of the diagram, so ignoring the isosceles 3-3 bit of the triangle, on the left there's part of that triangle where the side lengths are 5 and 3 and there's an angle of 30 degrees. Now if you write down the cosine rule, things will sort of check out. You can find the value of C, but it turns out that there are two solutions. So you might have a picture that looks like the triangle on the left, and you want to find that length C at the bottom, but you find two positive solutions, two plausible values, and that's because of the triangle around the outside of that diagram. There's this kind of other triangle where going around the other side, so going around the outside of the diagram, you get this larger value of C. One way to think about this, so this is the case where you're given two sides and an angle that is not between those sides. So one way to think about what's going on here is the kind of trigonometry that someone was talking about before. So you're given a side length, let's switch back to Mario, given an angle and two side lengths, this side length, B, and then another side length for the side over here. So maybe that's, I'm going to draw it off at an angle like this, like A. There are several possibilities. So I'm sort of imagining this. We're told that the triangle has a side length B over here, a side length A over here, and an angle alpha down here. If A is too small, then there's no solutions at all. If A is just right, then there's an angle I can choose up here that sort of perfectly makes a triangle. So there's sort of some hopeless lengths for A that get there. There's this interesting A in here, which is just the right length that I get a solution for this triangle. A again, A opposite alpha, side B along this side. If A is just a little bit longer than that, then I get two solutions. I'm drawing these circles of points. The information is the side of the triangle is A, which means it lies, the corner lies on some circle of distance A from that point. So there might be two solutions, and then the reason I'm talking about positive solutions is that if I make A too large again, it's basically like the diagram we were just looking at. If I make A too large beyond there, then there are two solutions, but they're not both positive. One of them involves a kind of negative length for C over here, which I don't want. Why are the two solutions to the quadratic guaranteed to be positive? So if you have all three of these facts, then you have a lot of clues. You have a mystery investigation, I suppose. This fact, because it is the discriminant, tells you there are two solutions. But why are they guaranteed to be positive? Well, if you're told both of these facts, then you look over here and you go, b squared minus a squared must be positive. That tells me that the product of the roots, why did I cross this out? This tells me that the product of the roots, like having this 6 in here, the product of the roots is positive. So I need to have either two roots that are both positive or two roots that are both negative. Those are the only cases if I'm just thinking about positive and negative for the two solutions, or roots of the equation, I suppose. Roots of the polynomial. So that's evidence. I've got two solutions and they're either both positive or both negative. And then if I look over here, there's a final clue, which is if alpha is between 0 and 90, then cos alpha is positive. So this term here, which represents the sum of those two solutions, will also be positive. I'll sort of trace it back again. Can I show you how the triangle relates to the quadratic? Yeah. Okay, so different cases down here. Different cases down here where I've got a fixed length B, a fixed angle alpha, and then this side length which is sort of not the other side of alpha. If it's the other side of alpha, everything's very straightforward and boring. But because it's over here, then I get these cases where it's too short, a perfect case where it's just the right length, which, by the way, is B sine alpha, which somebody said in chat ages ago. Some interesting cases where A is a little bit larger and you get two possibilities. That's called the ambiguous case, because there are two triangles that have the same length, A along here, B along this side. Let's draw one of them. So one of them looks like this. That's got a side length B, a side length A, and an angle alpha down there. And the other one looks like this, which has a side length B, a side length A, and an angle alpha down here. But they're different triangles, they're not congruent. They've got, one of them's got an obtuse angle, and the other has an acute angle for the side opposite B. One way to think about this is the cosine rule. So the cosine rule, if you like, is an expression for the quadratic for this side length, where I can write down the cosine rule using this angle. So I've got this side length C. Is it this much or is it the big one? Question mark. So the cosine rule will say opposite side, opposite the angle, A squared is B squared plus C squared minus 2BC cos alpha. And then this rearranges to say 0 is equal to C squared minus 2B cos alpha C plus B squared minus A squared, which is the quadratic we had before, but with X instead of C when we saw it before. So sort of related by the cosine rule. There's another way to think about it, which is the sine rule, which says that sine alpha over A is equal to sine beta over B. Beta will be this angle, or maybe this angle, for the angle opposite B. And one way to think about this is that sine beta repeats values. So you get these two possibilities. That even if you know the value of sine beta from your expert knowledge of the sine rule, you know the value is something like B sine alpha over A, but then there are two possibilities. Two possibilities of what that angle might be, which in this case corresponds to two different triangles. Aren't those three statements necessary on the roots being positive? Mames Jonro, hi, good to see you. Each of those statements is necessary. All of them together is sufficient. So between them, they are necessary and sufficient. Neither of those precludes the other. That statements can be necessary and sufficient. In fact, that's the dream. That's what we want. That collection of statements together, circled in purple before, that collection of statements together captures precisely the cases, precisely the triangles where it's ambiguous, and you get two possibilities for the shape of the triangle, given this misleading side-side angle situation. This happens precisely in the cases where all three of these facts are true. So side-side angle is ambiguous if the angle is acute and the side that you're given that's not opposite the angle is larger than the one that is opposite the angle, and the side that you're given that is opposite the angle is less than, or is it? No, last one is the side you're given that is opposite the angle is larger than the height you would get from a right-angled triangle. I think someone in chat was talking about the other side of the triangle. There's these effects like b squared minus a squared and things going on for a length in this picture, in the sense that as the circles get larger, they will touch this line somewhere, and then you'll have briefly 2 points, and then one of them will be too far over here and won't be part of this line segment. This is the SSA case. It is the ambiguous, the only one that goes ambiguous. It's why people say not to use it as a congruence rule. What I'm trying to prove on the board is the slightly harder technical thing, which you almost certainly don't use in school, which is that if any of these three statements don't hold, then this is actually not ambiguous. There's at most one triangle that satisfies all those conditions. So, like, possibly the thing that you learned in school is that if you're told two sides of a triangle and an angle that's not included between them, then it's always a problem. It's ambiguous. But reality is not that straightforward. The correct thing is that if you're told two sides of a triangle and the angle that's not an angle that's not between them, then that might be ambiguous. It depends whether these three conditions hold at the top. Good, right, okay. I forgot to look at the song. I was recommended a song a week ago. And then like an idiot, I spent the week getting ready for the open day and stuff rather than looking at the song. Right, okay. Where do I write this? Notes. Right, I've been talking about the warm-up problem for half an hour, but I think it was good fun. So, you know, there you go. Let's chat about drinking. Okay, good. Bye. Okay, right, fun. I enjoyed that. Different ways to think about the ambiguous case of the sine rule or of the cosine rule, depending on how you think about quadratics. If that seemed interesting, then we can talk about the revision question that is about this, but we're going to do a vote. So I need to go to Slido. How do I go to Slido? It's over here. Revision questions. Pop. So this works as a vote. There are 15 of them this week. Let's have them on screen as well. Let's hide chat just while they're voting. They can see chat, they can do things over there. So the revision questions cover a range of things. Partly they're about solving equations using trigonometric functions. There's sneakily a geometric progression in there. There's also some sort of angle expansion facts, just in case anybody wants those. But then down here, where is this? 11 and 12. 12 has got the interesting phrasing about find all possibilities for the remaining side length. Saying maybe there's more than one. And then there's something we're using the sine rule for the ambiguous case. Right, okay, from the cosine rule, yes, I'm going to prove the triangle inequality. Eisenstein triangles at the end. Let's find out if anybody wants to talk about any of my favourite questions. Currently winning in the Slido vote are 10, 7, 11, 12, 1. Okay. 1, I reckon you can do question 1. If you draw it carefully and you think about the size of the triangle, drop a perpendicular down the middle, I think you'll be alright. I hope. Okay, we're going to do a little bit of time for voting because I think people are still voting. Question 10 is still winning. Yeah, there's all sorts of facts going on there. Yeah, I like this stuff. Good. Okay, let's move some paper around. Right. Okay, I think I'm going to do question 10. There's voting going on for 11 and 12 and 7, so that gives us a nice sequence, doesn't it? We can do 10, 11, 12 to start off with. Okay. Chat's going to join in as well, though, because I've been talking a little bit too much. So we're going to try and balance that out by asking chat to join in. Finish your voting. Last chance to vote. 10 seconds of voting. Let's find out what chat's up. Yeah, good. Okay, I think that's voting. Thank you, person who voted right at the end. 10, 11, 12, 15 has just pipped in as well. Good fun. 15 is the cosine rule. Let's see if we get there. Okay. Chat, see if you can help. Oh, you're not covering up the question. That's a good start. This question is about simplifying trigonometric expressions. It includes things like cos of 90 minus x, sine of 180 minus x, sine of there's sort of everything going on there, sine of 90 minus x. To make it more fun, question 10 says, some people learn a thing in the formula booklet which just does this question for you. There's an expression for sine a minus b, which is not really what I'm up to, but you expand sine of a minus b or recognise sine of a minus b. That's not really what I'm trying to do here. I'm trying to get you to practice all of these rules about sine and cosine. So here the question says, it's sort of in a teasing way. If you know a fact about sine a minus b, you may only use it here if you prove it. And I didn't really intend that to be the idea for the idea that you would actually prove it. I wanted you to use some sort of relatively more basic stuff. Do we need to know year 2 trigonometry? No, I don't think so. It depends. I don't really know whether you learn things in year 1 or year 2. That varies a little bit. The trigonometry that you need to know is precisely the stuff that's in the TMUA specification. I've got that in my notes. So if you get the worksheet that's over the screen there's a list at the front. There is not quite half a page of trigonometry at about half a page of trigonometry that you need to know at the top there. Not very much. Geometry had quite a lot last week, but I'd be surprised if this was year 2 stuff, really. Value of cos of 30 degrees, I think you probably learned at GCSE or equivalent. Right, good, okay. Where are we going? I've done that thing where chat has the black bar. How would you actually prove sine a plus b? Oh gosh, I think the way I know uses complex numbers, and I know a different way that uses a very complicated diagram, right? So I would try not to, even if someone gave me the choice. I think I would prefer not to draw this diagram too many times in my life. I think I have drawn it before, and these are both ones, so you can work out lots of coordinates of different points by using some sort of dropping the perpendicular and finding lots of distances. I think I've done that once in my life, which is probably enough times. Then I found out about complex numbers. It was great. No complex numbers on TMUA. What are we doing? Oh yes, we're doing question 10. People have asked for help. We should help with question 10. So there are many terms in question 10. Let's see if I can get all of these right first go, because some of them should remind you of facts that you know. There's relationships. Joining together angles in circles and triangles and things. So maybe when you see this, you know that this is sine x, because, well, partly because angles in a right-angled triangle that aren't the right angle add up to 90 degrees, but also partly that's one of the rules that maybe you would just get told at some point about cos and sine. The thing I've got in mind, the kind of mental image if I want to remember a fact like this, is this, where those angles add up to 90 degrees, you see, and from the point of view of one of them, this is the adjacent, and this is the hypotenuse, and from the point of view of the other one, that's actually the opposite, and this is the hypotenuse. Depends where your point of view is for a different angle, so it's opposite than 90 minus alpha. Have I done that exactly the wrong way around? I've done that exactly the wrong way around. I think I've made my point. Depends which angle you're looking at. That's my mental image. It's a bit mental. What else have I got? I've got sine. Gosh, making a meal of this 180 minus x, where I suppose really I kind of need you to know that sine looks like this, and 180 minus x is, as x is increasing, this starts at 180 and decreases, so x is increasing, 180 minus x is coming down. This has got a line of symmetry down here. Sine. So this is just sine x. Similarly, both of the other ones are cosine. Oh no, with a minus sign in the middle. Because cosine's got the opposite sort, hasn't it? Cosine 180 minus x, there's a minus sign because it's going up from -1 instead of down from 1. Which means that overall you get cos squared and sine squared. Let's write those out. This is the one I was thinking of when I drew my triangle. It's almost the same fact, right? Never mind. And then this one, so as x increases from 0, that's like starting here and increasing. 180 minus x starts here and decreases. So we have increasing x, decreasing 180 minus x. Cosine maybe looks like this. So if I'm 180 minus x, that means you started at -1 and you're increasing up. Turns out this is minus x. So the stuff in the question turns into sine squared plus cos squared. What's going on here? Are we allowed to use? You can also change. Oh, graph transformations. Good idea. Yes, if you know that these graphs are secretly the same, right? I don't know. Do people know this? That the sine graph that looks like this and the cosine graph that looks like this, if you put one of these on top of each other, they're the same shape. They come down from 1 to -1 in exactly the same way. These graphs are just exactly the same as each other. I don't know. I sort of feel like that's always a conspiracy or something, or I don't know, secret information that the way it rises like that is the same for both of these curves. Got to put it back, otherwise who knows what I'm talking about. Right. Okay. I don't know if we can do this. Right. Okay. Can we construct a matrix with this as an element? Oh, I see now. It's the group rings person. Well, there you go. That's narrowed it down. Okay. What else is going on? So question 10, kind of testing 4 different identities all at once, and then secretly sine squared plus cos squared right at the end. So that's equal to 1. If some of these are a surprise to you, then I think I would encourage you to think about triangles like this, which I guess only works for acute angles anyway, but think about what you can say about that triangle to help you convince yourself that some of these are true, which might help you prove to yourself that this bit of the curve is the same but backwards compared to this bit of the curve. And from there, because they're so symmetric, you can do a lot of stuff to convince yourself that, yeah, this is fine. Those are basically the same shape. Good. What else is going on? Quite a lot of else is going on. People also wanted to talk about 11, which is also on screen, which is nice because it means I can just leave it there. 11 and 12 are both going on. Let's do this carefully. So there's a difference, right? They're almost the same question, except the bit that says BC equals 7 changes to say AC equals 7. And you need to know when it says angle ABC, I like to include this angle symbol. I've noticed that TMUA normally does not include this symbol. They just say angle ABC. Or occasionally, and I don't love this, but they say the angle B to mean the angle that's at B. So my preference is to label angles with lots of symbols and stuff. Anyway, just a little bit about notation. Where are we at? That means the angle at B, the middle one. The one from A to B and then B to C. Whatever. Yes, it was 1. Sorry, it was 1 in the end. It all simplifies down. It was beautiful. It was sine squared plus cos squared. There's a nice reason to do with the stuff that other people in chat are saying about things in the formula booklet and identities. There's some shortcut to realise that it's going to be 1 without working out all 4. But the reason that's on the revision notes is that I kind of want people to practice all of those different identities that we had up there. I'm sort of trying to test that you can recognise stuff and use it and simplify things using whatever you've got, rather than necessarily that you know lots of advanced mathematics, double angle formula or whatever. Okay, so cosine rule. This is a good demonstration as well of angle congruence or something. So in both questions 11 and 12, we're given two side lengths and an angle, but changes which one we're given. So AB, maybe that's this side of the triangle. And then in the first question, question 11, we're told that BC is 7. And we're told that angle ABC is pi by 3. So we've got two lengths and the angle in between them. This is side angle side. There is only one triangle that does all of these things, up to rotation and reflection. This is the only triangle that does all three things like that. Okay, which means that you can use the cosine rule. The cosine rule is great for working out the other side length because, well, the rule is something like, what is this? Should I call it B? Because it's opposite angle B? Well, I don't know. 8 squared plus 7 squared minus 2 times 8 times 7 times cosine pi by 3. I'm using radians for this one. That's 60 degrees, isn't it? So cosine gives a factor of 1/2. So things are quite nice here. But anyway, you sort of work out the number over here. If you've not met the cosine rule before, I think we've got a couple of Year 11 students or younger in here. If you've not met the cosine rule before, it's kind of incredible relationship that's a bit like between the side lengths of a triangle. It's a bit like the first bit reads like Pythagoras' theorem. Square on the other side is equal to the sum of the two squares, but there's a correction term, there's an extra bit to allow for cases where it wasn't a right angle triangle. It's got this cosine angle term in it as well, that helps you work out the actual length of the side if this is not a right angle. You're changing that angle, you get different lengths of the side. There's a formula. It's brilliant. Anyway, I think it turns out to be 57 on the right, so everything's fine. Question 12, let's see if I can fit this on here as well. We're told once again that AB is 8, but this time we're told that AC is 7, which is the angle opposite this pi by 3 thing. So how do I draw this? Well, maybe something like this, where this length 7 is opposite pi by 3. And this is now SSA, wiggly, whoa, so the cosine rule this time gives, it's a different side that's unknown. It's this side A that isn't known, opposite the angle at A. And I don't know that angle either. So the cosine rule gives something like 7 squared for the angle opposite, sort of swapping the angles around, right? 8 squared plus A squared minus 2 times 8 times A times cosine pi by 3. And now instead of, behind my own face, sorry. Instead of having a nice simple expression which is equal to B squared, doesn't even read as a quadratic equation, does it? But it is. I now have a quadratic equation that involves A squared and A, and it turns out that this has 2 solutions. So there are 2 possible solutions to this. I'm looking at my notes because I don't think I want to run through and actually solve for all of these. It turns out to be either 5 or 3. You've got choices about what to put there, which is maybe a bit of a surprise that you have 2 solutions. Well, why is that? What's going on? It's because as well as having a triangle that I draw like this, there's another one where instead of having a length of 7 going that way, I have a length of 7 going this way. 7 is large enough to reach this line that's going on. Not so large that it's larger than 8 and has a solution over here, so there are 2 solutions kind of nearby. So the quadratic has solutions 3 and 5. Right, good. Okay, quadratic equations. So solve 2 positive solutions. We thought about that earlier. 3 and 5, which is quite nice, isn't it? I don't know. It's sort of nice to see it happen for some particular numbers. I claim if you go and plug in, factors of 1/2 or whatever, they're going to turn the handle and work out what's going on for this quadratic equation. It's a little bit tough, isn't it? You'll need to square 8. That's 64. Good. Right. Okay. Any more for any more? We're pausing slightly. Oh, the geometric sum. Did we have this before? Ooh. If I included this on 2 question sheets, feels slightly Groundhog Day. I'm going to scroll up to it as well. I feel like I've been here before and shown you this geometric series. 1 minus sine squared plus sine to the 4 minus sine to the 6. Interesting. Sadler's went over to New College, but I'm stuck in the department. So I was in the department all day. That's right, okay. I think in the sequences question, I used this question in that one as well. Revision. No, different series, no signs, but another tricky geometric sequence question. Found it, right? Good. Okay. We did talk about previously on this office hours live stream show thing. We have talked about tricky examples using this sort of geometric series, but not exactly that one. Good. Yes, things went a bit wrong there, didn't they? No, we were all right. Sanders, presumably you met one of my colleagues, like maybe Victor Flynn or Sam Cohen over at New College. I hope you had a nice time over there. Yes, I've managed to blink everything. Sorry about that. That was one of those times where something went wrong and people noticed that something went wrong. 7, we're doing it. So if this sort of infinite series is new to you, it's a thing that you learn about at A-level at some point. The idea, maybe you haven't met it yet, but it's coming up near future if you're doing A-levels to learn about sequences like this with a ... where there's a pattern to the terms. At A-level, you at some point find out that there's only really one style of this where you have to be able to recognize this, which is where you have infinitely many terms, but each of them is related to the previous one by some common ratio. So this is multiplied by something, and then this one is multiplied by the same thing, multiplied by the same thing. In this case, minus sine squared x. And then at A-level, there's a formula to say that if that ratio is between -1 and 1, then your terms are getting smaller in size. And a fact that's not proved at A-level, but is true, is that adding up all of the terms, infinitely many of them, it's not a thing you can do, is it? But the more terms you add, the closer you get to. The formula for this is a over 1 minus r, where a is the first term and r is this common ratio. So in this question I need to write first term divided by 1 minus the common ratio. Not too bad at all. Depends on x, I think. Although there is a question there that what happens? There's an exception. It was Sam at the Meet Your Tutor says, Daniel, oh look, several people have been over there. And Dexter was confused. Sorry, Dexter. Right, good. What do people wear on maths courses at university? There's a bit of maths t-shirts. There's not a lot of suits. There's a bit of casual wear. A bit sort of like normal clothes. You're talking about our actual students. Yeah. Much more towards the kind of maths t-shirt end of your 3 options, Bob. Good, right, okay. So this is really secretly, this kind of maybe should be on the question about sequences, because once you spot the common ratio, it looks like those sequences that we saw on the sequences episode. there are other ways to do this. Maybe you read this and you read this much of it and you thought, aha, cos squared. And then this is secretly, if you bring out a factor of sine to the 4x, it'll be that times 1 and that times minus sine squared. Aha, 1 minus sine squared is cos squared x. In which case you also get a geometric progression for which you would like to add infinitely many terms together. In this case, the first term is cos squared x, and the common ratio is sine to the 4x. And then, I suppose, beautifully or something, difference of two squares down here. This is sine squared squared. This is going to turn out to be exactly the same thing. I hope. I mean, it sort of has to. So this 1 minus sine squared here is equal to cos squared, which leaves us with 1 over 1 plus sine squared. So different roots to the same thing. In this case, I'm thinking of this cos squared as my first term, and the common ratio here, this is multiplying by sine to the 4, and I am sort of confidently asserting that will happen again for the next two terms. You might like to think about that. Good. You don't need to get a maths t-shirt to fit in. Although, yeah, I know I've not worked out what's going on. Right, good. Okay, there exist maths t-shirts out there. Goodness me. Right. Okay. What's going on? We've done some revision questions. We've done, I think, we've touched on this ambiguous case. I maybe spent too much time on the ambiguous case of triangle congruence, but I think it matters. It's interesting as well. That appearance of the b sine alpha term. That's cool. And we've done some practice questions where we thought about cosine rule a little bit. I'm not sure we've talked about the sine rule very much. Maybe that's okay. If there's anything from the revision notes that people want to talk about, then we can do that now. But my suggestion, because it's 6 o'clock, is that if you've been looking at a screen for the last hour, it's probably a good moment to look away from the screen, blink, and I'm going to drink some water. You're welcome to do the same thing. Right, cheers. Okay, what else is going on there? Well, we've got some TMUA questions, if we keep scrolling. If you're new to the live stream, the worksheet comes with TMUA questions, which say something like, see the next page for hints. The hints are designed to help you if you don't want to look at the solution, which is good, because looking at the solution will ruin the question forever. You won't be able to go back and pretend you haven't seen the solution. Not to yourself, anyway. What am I saying? But maybe you want to have some advice. Maybe you've got a teacher or someone else who can help you with TMUA questions, but maybe not. In which case, the hints are supposed to be there to nudge you in the right direction to get towards those. How do you join the live sessions? I think you're currently in the live session. Possibly you're in Slido. Right, okay. Let's go. Hello. We're on YouTube as Oxford Mathematics Plus, just in case. That's a new one for me. And then hopefully they'll find the page as well. I mean, if they've found the Slido, they've probably found the thing. Right. Do I think England will beat Mexico on Monday? Goodness me. They've not given me a lot of confidence in the game so far. Let's go that fast. Depends. Is Harry Kane going to score another 2 goals? That'd be a good start. Right. Okay. Enough football. Here is. Oh, what's the conversion between radians and degrees? That's a good question. We're going to do a bit more voting. There are 6 TMUA questions that we might do. And I'm going to tell Dexter what radians are. Let's hide chat, even though you're doing some voting, and switch on the voting. 6 questions that you might want to see. There's this one, which asks for 3 cosine x to be equal to the square root of x. And the hint, I think, is that you should not try and work out what the value of x actually is for that. But you can still reason about when these things happen. I see this question says that x is in radians. For people who haven't met radians yet, the difference is that instead of having 360 degrees in a circle, radians are quite a bit larger. The number in a circle is 2 pi, 2 times pi, which means that on a straight line, instead of saying 180 degrees, you say pi radians. If you see 90 degrees, then you say pi by 2, pi over 2, or pi by 2 radians. That's it. It's sort of almost a madly simple idea. The advantage is 2 pi is something to do with the circumference of a circle. So when you're measuring bits of arc length around the outside, bits of circumference, radians are very convenient for that problem. And then they turn out to be much better than that. But for TMUA, that's about it. 2 pi, I mean, it's stupid, isn't it, right? 360 has all of these nice factors. 2 pi, not even a whole number. So, no factors. This paper question from 2021, we can talk about it if you like. It asks for the maximum and minimum values. Well, I mean, it asks for the difference between those things, but you're going to calculate the maximum and minimum values. Possibly you know enough maths to just differentiate that function and find the turning points. If you do, you could do that if you like, but the question is a little bit easier than that. You can probably do it faster using methods where you don't need to do the chain rule and the product rule and the quotient rule. Other maths is available. See if you can simplify the function first before you do anything clever with it. Further down, we have a question from paper 1. So here are the hints. Let's go past the hints. A question from paper 1, which looks at this kind of compound function, sine squared of 4 to the cos theta times 60. Oh my goodness. So several things happen, right? Theta goes through the cosine function, it goes through the 4 to the x function, it gets multiplied by 60 degrees, and then it goes through sine, and then it gets squared. Goodness me, what values, when does that happen? But the ones people are voting for at the moment are the paper 2 questions, which I'm pleased to see. For example, there is this one, which doesn't even quite fit on my screen. But this is a question where a student chooses real numbers x and y, and then uses those as the values of sine of some angles in a triangle. And we're asked, essentially, how many different triangles are there? Which is the ambiguous case, I think, of something. But it's not the standard ambiguous case of the SSA situation. We're not quite in that case. So there's something else going on in this question. Good fun. Paper 2 has got this kind of thing. Often there are words in bold. Often you're required to think very precisely. These statements have this statement structure, to say for some choice of x and y, there is exactly. So sometimes I think paper 2 of TMUA is a bit like paper 1, but they say exactly, and they put words in bold to make sure that you're doing precise mathematics. We'll talk about this question using ideas about what it means for sine A to be equal to some number x. A hint, it doesn't tell you precisely what A is. And then people are voting a bit for this question, or hints. This question down here, which is very clearly two non-congruent triangles, right? It's the ambiguous case. Put them together. These questions about ambiguities to do with triangles. You're given some information about a triangle, but that does not, in some cases, tell you what shape the triangle is. Sort of feels like you should always be able to work out what shape your triangle is. It's triangle shaped, but you know what I mean. Not all triangles are the same shape as each other. And then lots of votes. I'm pleased to see this. Lots of votes for this brilliant question from paper 2 in 2022, question 20. So many twos. Look at that, brilliant. Which involves applying cosine and sine lots of times, using radians, but sort of matters a bit, I suppose. In fact, that one's winning the vote at the moment, so I'm going to give it a second. We've got about a dozen people voting. I'm going to have a quick look at chat to see what's going on over there. If you get rid of pi, how do you calculate area and volume? Well, yeah, in some sense, if you could calculate area, then you would rediscover pi. I don't really know what get rid of pi means. Yep. And then Jamie would like to know what we want for TMUA. We want as good as possible on TMUA. It's our first year using it. Kelly's pointed out in chat. And we're not going to set a hard pass-fail mark anyway. So trying to help people just get as many marks as they can in TMUA. For example, this question, which I think is now, let's call it there. So 6, then 4, then 5. That makes sense. Paper 2 questions. Good. People have, when I tell people about this, people have sometimes been asking me if there's a special section on logic or reasoning or paper 2 or something, and we're trying to put that all the way through. As you know, because you are here and you are voting for it now. Why am I advertising this show to you? You are here exactly now. Right. How am I going to do this? I've got these functions, but what I really want to have on screen is the options, because the options are really interesting. The functions have got maximum values M1, M2, M3, M4, and M5. This is going to be the perfect question to do. Following that conversation earlier about squares, right? Yes, can I find that old algebra question? Yes, let's see. So warm up. I know we've done warm up already. We've done warm up already, but here's a little bit more. If -1 is less than a is less than 2, what can you say about a squared? So a squared has got this kind of folding nature to it. It takes positive numbers, it makes them into large positive numbers. It takes negative numbers, it makes them into large positive numbers. Oh, so it sort of takes the number line and bends it around like a bakery. They have to fold bread over, but everyone always says that for everything. So, in a bakery, you have to fold the thing over, making a croissant or something. One more person has voted, but they voted for, I think, the same question. So we're good. Good. Okay. So there's this question on an algebra sheet or something somewhere. I can't remember where I've put it. Where sort of the obvious answer that's wrong is 1 less than a less than 4, which is no. Squared. Which kind of feels like it should be true, right? Well, a squared should be between 1 and 4 because a is between -1 and 2, so you square it. But this is not the right answer. Daniel in chat has got a closer answer. That's still the vote. I haven't actually turned it off. 6, 4, 5. Because on your number line, yeah, there you go. You picked it up. Perfect. Daniel got that. Good. Okay. On the number line, -1 is not included. 2 is not included. And then x squared will look like this. And that does include 0. So the correct answer is 0, less than a squared, less than 4. This kind of thing where it's folding over the number line, and you get extra stuff. And in this question, we're going to apply functions like cos and sine. And they have this ability to sort of fold over the number line as well to repeat values. Maybe that's relevant, maybe not. I just thought you'd like to see it. This idea that, weirdly, it's got this less than or equal to sign in, which no one ever sees coming. What's the technical word for this folding thing? The function is not 1-to-1. The squaring function on the number line is y equals x squared is not 1-to-1. That's a relevant fact about x squared sometimes. It's not 1-to-1. University, there's this word for this word injection for the property that function doesn't have. Anyway, never mind. Anyway, right, I could talk a lot about that because quite often you want to just get on with it, right? And just say, right, okay, but if they're positive numbers, then everything, none of this is a problem if they're positive numbers. It's all fine. If they're positive numbers, you can try take logarithms of both numbers, and that's also fine. Sort of 1-to-1, strictly monotonic functions, all lovely. Right, let's see how that goes with cosine and sine, which are not one-to-one functions. Maybe that matters. Let's see. Okay, so to start off with, I'm going to track the minimum as well because I am worried about decreasing functions. If I just track the maximum, then when I apply the next function in the list, you see how each one asks you to apply another function. If one of those is a decreasing function, then the biggest output, just like this, the biggest output will come from not putting in the largest value, but it will come from putting in the smallest value. So I should track the minimum as well, just in case. Okay, so f1 has minimum value -1 and maximum value 1 because it is simply cosine. Doesn't matter if you use radians or degrees, the minimum value is -1, maximum is 1. Let's see how much if I can bring everyone with me. So f2 asks us to apply sine to all of those values. And you see how this is a bit scary, right? Because, like with squaring, it would be very tempting to just write down sine of -1, sine of 1. But I've got to worry a little bit. Like, does it have some sort of turning point in there? Does it have some turning around? In fact, sine of -1 and sine of 1 is in fact the correct thing to write down next. But I want to try and show you what might go wrong. If you put some range of values on the number line, f1 could be anything between -1 and 1 inclusive. So we have this kind of like true fact that -1 is less than or equal to f1 is less than or equal to 1. Jamie's got a great question. Can a function be one-to-one but not go to everything? Yes. Your function can be, using the language of Introduction to University Maths, which is a course that I teach at Oxford, your function can be an injection but not a surjection. You don't need to know these words. It's just amusing to me that you are asking the questions that are answered in the course that I do when people get to Oxford. Brilliant. You come to Oxford and I will tell you that again in a lecture. Brilliant. Right. So here's the thing I'm worried about. We're putting a range of values into sine. And sine looks like this. So if you put a very large range of values into sine, then you get to this bit, which looks a bit like x squared, doesn't it? Or that bit, which looks like -x squared, which is just as bad. So if you put in this, if your plan is to enter this large range of values, then the values you will get out will be these values of sine. Well, you see how the problem is, right? Like if I just read off the endpoints, then that's not the maximum, it's not the minimum. It's just some sort of like random values because the maximum might not be achieved at the endpoints of the interval. If I say it like that, then I mean why would you expect the maximum to be achieved at the endpoints of the interval? Normally, when you have like an interval, like you have some interval and you have some function, like the maximum achieved at the endpoints. Oh, it is in this case. Well done, me. Great example. Anyway, never mind. Some range of values and you apply the function. Maximum could be in the middle, could be somewhere else. In fact, this is not problem here, because the endpoint 1 is less than, we're using radians, so this is at pi/2. And the biggest value we're planning to put into the function is not that large. The biggest value we're planning to put into the function is 1. So back up a bit. Nice and boring. 1 is less than pi/2. Back it back down a bit. So none of these values. We're just going to put in relatively small values, like 1, which is going to lead to sine of 1 is actually not that large. Sine of -1 is not that negative. A bijection is any function that is a surjection and an injection. It's used for things being the same thing. by function be 1 to 1 and not go to everything? So infinity is weird. Infinity is really weird if you're dealing with infinite sets. But also just if your sets are different sizes. Sorry, I'm now just doing Introduction to University Maths with Jamie in chat. Sorry, I have some lecture notes on this. If you search for Introduction to University Maths Oxford, you can find some interesting notes. You can do 1 to 1 if the set that you're going to is very large, then you can be 1 to 1 by not repeating any values. But the set you're going to is so large that you don't explore all of them. And if the sets are infinite, then that's anybody's guess. Anyway, this is diagram over here. It's trying to show you what could have happened. There's an extension question to explore what really might happen if I double some things. But minus is supposed to be a justification that I can sine 1 over here and sine of minus 1 over here. Which is what you wanted to write anyway, I think. So, what am I doing? What am I doing? Oh well, never mind. This is great news. I found M2, maximum of function 2, and I've had a nice chat about set theory. Right, okay. Where are we going? F3, next one. So next job is we apply cosine to those values. And this time, being careful pays off. Because cosine, it's going to be funny, isn't it? Cosine looks like this. So that even if you put in quite a small range of values, and sine 1 is really not very large. I mean, it's less than 1 because it's sine of something. 1's not a very large number. So these numbers that you're putting into the function, even if they're quite close to 0, well, we've got that like x squared shape, haven't we, right? Upside down, right? Where the endpoints will mislead you. And the correct things to write down in here are not, the maximum is not cos of sine of 1, and the minimum is not cos of minus sine of 1, and you should be suspicious if you write those down because those would be the same. Yes, aha, right. So M3 in chat is the number 1 because of like that square thing, right? That it achieves the value 1 when you put in 0. I suppose you don't put in 0, you put in whatever gave you 0 from the previous function. So I'd like there's some possibility that F2 equals 0. Which will lead to F3 being 1. How do you get to F2 being 0? Is F2 of 0 when F1 is 0, which happens when the angle is pi by 2 or something. Oh, amazing. Okay, like a chain of things, right? You have to work backwards to work out what x is. Well, you don't actually have to do that, but good for tracking the range. Anyway, good. Okay, so the maximum, but then from this shape and from the fact that the numbers are quite small now, sine 1 is even smaller than 1, this minimum value, and it is a minimum, not a maximum, at those endpoints comes from blob, comes from putting in sine 1. This is cos of sine of 1. I don't know how large that is. I think it's pretty close to 1. Looks a little bit less than 1, but not that much. Okay, F4 still to go, but same ideas now. We've now seen sort of all of the problems that might happen. We've got some range here, which is pretty close to 1. It's not a very large number. And the lower limit is not 0. So our next plan is to apply sine, but sine at this point is just some sort of like well-behaved function nearby. It's not doing anything funny. It's cosine that I'm worried about. I should be looking a little bit at the options. So if we're playing along by looking at options along the way, totally relaxed about this sine actually. Just going to go for this. These are small numbers. Sine for small numbers just looks like almost like a straight line. If you're playing along with the options, so far I have discovered that option A says all of them are equal to 1. I don't believe that. This is my right-hand column of maximum values. Option B says M3, I don't know about 4 and 5 yet, but M3 is less than M2, which I disagree with. And at the moment I've just got down to M4, and I think it's equal to M2. So I don't like option D, and I don't like option F, because they say M4 is less than M2. I've got the same maximum, M2 and 4. So the only thing I need to decide is between C and E. They're the only ones live for me, where they've got M2 equals M4, And it looks like the question is going to be, is m5 1 again, or is it something smaller? So I like to track the range of the function if I'm going to then make that be the domain of my next function, rather than just tracking the maximum. I think that makes sense, right? If I said, I've got this machine that squares numbers, I'm going to put lots of numbers in, they might be positive, negative, or zero. I would like you to tell me what the largest thing that's going to come out of this machine might be. So I've got numbers on the line that I'm going to put into the x squared machine. Shall I just tell you the largest number? Or do you need more information than that? If you want to see the largest output from the x squared machine, you want to know which one's going to give you the largest x squared. If I just the largest ones is 6 is the largest. You kind of need to know as well what the smallest is -7, one of the numbers, right? It's got a larger square. Oh, yeah. What is C? Yeah. Some people call that image, which is the confusing thing. It's annoying that we haven't quite agreed. And possibly I'm using it the wrong way round because I'm talking about the... No, I think I'm fine. I'm using one of the accepted uses of the word image. Right, okay, F5 to go, and then I've done this question very slowly, but that's partly because I'm doing it very thoroughly. I'm trying to do all of the little bits of it and tell you what might have gone wrong. I saw someone in chat say last time, TMUA is 2.5 hours, you've live streamed for 2 hours and you've got about 3 questions. That's not a good score. It's fair feedback. So also, I'm trying to do them really slowly. Well, we're doing M5. We're going to apply cosine to all of these values. And we're now in a situation where this range does not include 0. We had a symmetric range up here, and we applied cosine. But now down here, that's not a symmetric range. These are both just some positive values, I think. So we've got a range for our cosine now, which, unlike this nice symmetric picture, the numbers that we're putting in are over here somewhere. And in that range, everything is less than 1 is less than pi over 2. So cosine now, it looks like I've zoomed in quite a bit, I suppose. And we're plugging in these values. I'm using coloured in dots for when we're including those values. So now I can see that, well, this is positive, that's less than pi over 2. Cosine is actually quite well behaved here, and it's the case. Like that decreasing function I was worried about ages ago, the smallest number that you plug in gives the biggest output. And the biggest number you plug in gives the smallest output. So I'm not going to write down that one because I don't care that much. We're done now. But for the largest value, it's the cosine of the smallest input. I don't know what this is. It's a mess, isn't it? 1, 2, 3, 4 lines of nested brackets. But I don't also care about its value that much. I just care that it is not equal to 1 again. There's no way this can get to 1 because there's no way to plug in 0. Good, right, okay. So I think I'm going to pick option, which one's that? Is it F? I think it's F for me over here. Good times. Oh, E. Why have I got E? Did I eliminate E? Oh, I confused myself. Sure, I eliminated E. Whoops. Oh, I eliminated D and F, and I was left with C and E, and then I forgot which way around it was. I'm picking E. Good times. Right. Okay. TMUA question. Lots of stuff going on with this one. If this was interesting or new or weird, then I sort of think I want to give you example questions to think about, like the one on the extension in the solutions document. If you go to the website and get the solutions doc, talks about putting factors of 2 everywhere, which makes things a bit more exciting. But I think I want to get you to think about questions like if I have some range of values, like I don't know, if I have some range of values and I applied to some values with a less than x less than b, what happens? What can you say about the output? And it depends on the values of a and b, whether you will have less than or equal to signs, or equal to signs, or greater than or equal to signs. It could flip because that function is sometimes increasing and sometimes decreasing. I'm a bit sad I've put that on the screen. I think that might have actually been a fun interview question, but I can't use it anymore. There's so many cases to play with, right? It depends where A and B are, and you can explore all of them. Oh, I'm definitely not allowed to use that as an interview question. What a shame. What's the difference between codomain and range? Here we go. Introduction to University Mathematics. It's all available on... Is it on this YouTube channel? Yeah, we put the videos on this YouTube channel. You could watch all 19 videos on this YouTube channel if you want to. Pretty sure I answered that one there. Right. Let's do another one. Drink some water. Scroll. Oh, Sadler's in chat has found out about Skittles. Good times. I did do a Skittles video. I do a lot. I've done more than one video about Skittles. Just really like Skittles. Have I scrolled past it? No. That's the hints for question 18, which is the one they want. They want. Oh no, they want this. This one with lots of reading. That's what they want. Okay, lots of reading here. Let's do it bit by bit. So this is a question about, skimmed it before, a situation where you're told the length AB is 1. So it's a question about a triangle, and there are angles at A and B. The student's trying to draw the triangle. Sine A is equal to some value x, sine B is equal to y. Look right at the top of the question. It tells us that x is less than y. They're both between 0 and 1, and they're not equal to each other. That's x strictly less than y. So that's fun. Oh, I have what? No. Oh. Not something I spotted. Okay. Oh, can I get the extension question on the screen? Oh, I don't know. It's on the website if you want the extension question. I think I'm struggling to get this on the board. Look at this. Someone asked, can you get the extension question on the board? So I was like, oh, right, okay. I can try, I suppose. This one's got 8 options, which I do for TMUA questions sometimes. Here's the question. There's a big block of text there. Which of the following statements is/are correct? And because the words 1, 2, and 3 are bolded, the first time I looked at this, I thought, these sound mutually exclusive, right? Either there's one triangle, or there's 2 triangles, or there's 3 triangles. They sound mutually exclusive to me. But I realised that for different values of x and y, maybe the situation is it depends. And that's why these options have been written to say, for some choice of x and y, it depends what's possible, what might happen with different values of x and y. So realising to my horror that those read at first glance like they're mutually exclusive, either you get 1 triangle or 2 triangles or 3, but we're being asked for the range of possibilities. So these statements will be correct if the thing is possible. It says exactly 3 times. And then the options, there are 8 of them because 2 cubed is 8 for combinations. If you see a block of options like this, you should assume that all of the combinations are there. And sort of, when you're reading the question, maybe don't go through checking that all 8 of them really are. At a glance, that looks like somebody has written out the 8 possibilities for a label there. So, pro tip, they've probably thought of all of them, and you can't get an advantage by checking that they haven't skipped one and then picking exactly the opposite or something. Goodness knows. Right, anyways, which good news means I don't need to have them on the screen. We just need to decide, can these things happen? I, which, roughly speaking, is, can you have exactly 1 triangle for some values of x and y, 2 triangles, or 3? So I'm going to put the triangle set up there. I'm going to get myself some whiteboard underneath. I don't think we get the actual statements at the same time, but remember this. The question is, how many triangles could you have? There's a note at the bottom to say congruent triangles are considered to be the same, which it would make the question easier if that comment was at the top, because then you'd realise that they're talking about congruent triangles all the way through. The student can draw this triangle kind of anywhere, rotated around or reflected. But for congruent triangles, none of that matters, which way round they draw it or where they draw it, they've drawn it on the ceiling or whatever. So we should probably bring it down over here. And for my pictures, I've tried to draw this so that A and B are fixed. Because wherever the student has chosen to draw this triangle, I'm going to go, all right, okay, bring it to me. Translation doesn't matter. Rotate, spin it around, because rotation doesn't matter. Put it in front of me. A on the left, because reflection doesn't matter. For congruent triangles. Right, I'm ready to look at your triangle now that you've drawn somewhere. And it's got AB with length 1, which is a good start. Good, okay. Right. And then the mystery is, well, why doesn't this just specify the triangle exactly? You know, we're told the angles, A and B. And if you know the angles, then it'll be one triangle, won't it? Because you'll have this angle and you'll have that angle. The angle's called A as well, which is a bit exciting, but you know. So it really is, isn't it? So angle A and angle B, if you know both of those, you get one triangle. So chat, you tell me. I'm talking way too much today. You'd think I'd talk less after the open day, but I'm talking way too much. You tell me, why is it not just one triangle in all cases? Why is this a little bit ambiguous or a little bit confusing? We have different values of x and y, right? So you could have this. Oh, I shouldn't miss. Well, you're told the angle and the angle, they've got to be different. I've remembered that one of them is smaller than the other. Yes, in chat. Oh, I should put chat on screen if I'm going to talk to chat. There we go. Daniel in chat has got an idea. Let's see if any other ideas from people in chat. What else is going on? Let's see. Someone in chat with a username with doctor in it says that I showed them the institute. I wonder if that's someone who has done a PhD after I showed them around at some point. That'd be fun. What is going on? Daniel's got this idea about the sine function for ambiguity. Any more for any more? How are we doing? Triangles. Yeah, I think I like this idea really. That sine B has got two possibilities. That as well as having this possibility thing, I'm going to call them Greek letters. I'm going to call them, instead of angle A and B, I've decided it's getting a bit late. I'm just going to slip up unless I say alpha. Yeah, some people don't like Greek letters. I quite like Greek letters. Helps me remember that the angle is different from the corner, whatever. So we're talking sine value of sine alpha and we're talking value of sine beta. So actually there's another one, isn't there? That beta, it could be this angle, or it could be this angle. Those have got the same value of sine because those have got the same height if you draw in a little right angle triangle with the same size of triangle over here, same height. So beta could be this angle. Sine repeats values. That seems to be the lesson of today. Sine repeats values. And that's a problem because if somebody tells you sine beta is the value y, some number, then, well, there's two possibilities. A small angle and a big angle. A function, an angle so large that it's over there. It's got these two possibilities. And there's two possibilities over here as well. Is alpha like this, or is alpha like this? And so you've got this question like, how are you going to find this? Like, where are the possibilities going to take us? And for a moment there, I thought, well, now it feels like there are four possibilities, right? Because there's two on the left. They carefully told us that both of these numbers are less than both of these numbers are less than 1. So I'm thinking two possibilities. Two possibilities for alpha, two possibilities for beta, but none of the options in the question involve 4 triangles. So I guess some of these don't give any triangle. I teach at New College. I've just got a contract extension, so I can say that I will be interviewing for New College this year, and I'll be teaching students at New College for the next couple of years, which is very exciting. I spend most of my time in the department, but a little bit of time at New College. Good. Right, for only one triangle, alpha or beta will have to be 90 degrees. You can't be 90 degrees, right, okay. Oh, if there were a unique triangle, almost a complicated argument at the top, I like this. For only one triangle, alpha or beta, if it was going to be unique, then you'd need a right angle in there. I see. You want both of these to be the same. That happens at 90 degrees, but that's not allowed. So you think, not on. Sine alpha or beta cannot be equal to 1. Yeah, I like that. It's pretty good. It's in fact true that there is no value of x and y, no values of x and y that lead to exactly one triangle. I think it's kind of clear that whatever you set for whatever you set for x and y, there are acute angles alpha and beta, at which point it's fine. You draw the triangle that looks a bit like the one on the board, except I suppose I've got it the wrong way around because x is less than y. So I should draw my picture the other way around, shouldn't I? So the angle alpha is smaller. Let's do that now. So now I've realised x is less than y, which means that the bit from A is supposed to be less steep. This pair of lines representing this possibilities for, oh, I'm off the bottom of the page, too far down. Two possibilities for where that line's going. Is this alpha? This alpha? And then over here, two possibilities of beta. I'm supposed to draw a larger angle this time because the sine is larger. And one going off the other way, where the sum of those two angles is 180 degrees, which means they kind of have, like, because of the sine being equal in these two cases, like I'm drawing this like isosceles pair of lines, whatever that means. We have the equal, nice symmetric picture. However I draw this, with shallow lines on one side and steep lines on the other, I always end up with two possibilities, right? I have the one where they're both acute, and I have this one up here where there's an obtuse angle, but not too large. And then these lines, I've got the shallow one here, and I've got a steep one here. They don't seem to cross to give a triangle. And I've got the ones going in completely opposite directions, which aren't going to give me a triangle at all. They're not coming together, they're going apart. Not going to give me anything like that. If angles A and B are both obtuse, that's not a triangle. If they're both acute, we're good, both obtuse, no good. And then it took me much longer to realise that one acute, one obtuse might still be bad. Because in the case where I have one acute and one obtuse, I need the line for the obtuse angle to catch up. I need it to be steeper. I need it to have a larger value of sine, which means it has to be y. It has to be the angle at B that has that larger value. So I will get one possibility that these lines, because x and y are not equal, they're not even parallel, they're not coming together. Which means I get two cases, two different triangles in all cases. Which I sort of wonder whether I've missed a trick or something, that's the sort of punchline that I was expecting for the standard ambiguous case of the sine rule. Is two triangles. I suppose not all the time. As we saw at the start of this show, there's sometimes two for the sine rule in the original SSA setup. Anyway, weird question. We're told not the angles, but sine of the angles, and that means we're a bit ambiguous about what the angles actually are, but we can get there. Good. Okay, so I think two possibilities in any case, which I didn't waste any time thinking about how the options work here because it's kind of every combination. But I think I've ended up at C. I think it's always two. I wonder if there was a draft of this question which said something like, is it A, always 1, B, always 2, C, always 3? But now that I say that out loud, I realise that that question is very weak, because if you're told it's always 1 or always 2 or always 3, you can just try a case and find out which one it always is. If you're told from the options that it's always something, then you only need to check one to find out what's going on. Set X and Y to your favourite numbers and see what's happening. And a lot of this question is trying to disguise that fact by including all of the other possibilities as red herrings, or they're a bit of a smokescreen, so that the question is not telling you that it's always anything. So I think the question looks quite scary and looks quite long because they've gone to some effort to disguise the truth. But that probably shouldn't stop you from discovering the truth, right? If your technique is to try and not know any maths and just read the question and infer it from the things in the structure of the options or something, if you're trying to just bypass doing the question, then you're going to have a really bad time with this one, because there's brick wall here for what combination, because it's all of them, and the options are worded in this way. It's like, okay, it could be any of those when you read them. It could be any combination of them. But then we start drawing the pictures, I'm always getting 2. I think there's a good reason why I'm always getting 2. I'm just going to pick the one where it says it's always 2. Yeah, so y is definitely less than 1, because y is sine of beta or something. Yeah. So in both of those cases, different angles for beta, but sine of that angle is definitely less than 1. I kind of think of it as I'm given the value of y, and that allows me to write down 2 different values of beta and draw these 2 lines going off in different directions. Definitely not straight up, because y is not 1. And then those 2 straight lines will cross this very flat one at 2 different points and give me 2 triangles. Hello. There was a request in chat. If you're at the open day today and you saw a question with a parabola, there's a request in chat to see the answer. And if you give the points A and C sensible names, then this point, where the tangent is parallel to AC, has x coordinates equal to the average of the x coordinates of the other 2 points. That won't make sense to most of the people here, I'm afraid, because I haven't told you the question yet. At some point, we will do an episode about that interview question, but I used it briefly today for an interview. Used it briefly today for an open day. Didn't tell people the answer, which was mean of me, but you asked nicely. There you go, we did it. Okay, just in time. Hello, Tonto. Good to see you. Right, I think we've got time for a very quick look at one more, and it's the question that I found the hardest on this question sheet when I was putting it together for you. In fact, the sequence is that I found this question so hard that I went back to the revision notes and I added that big block about the ambiguous case, and I decided that I would spend a chunk of time at the start of this live stream talking about the ambiguous case, because it was looking at this TMUA question that made me realise that the ambiguous case is much more subtle than I thought. There's a lot more to think about, which I don't remember learning in school. A long time ago for me, so maybe I was told all of that stuff about the ambiguous case and forgot it, or maybe it just didn't feel that important when I'd got to A level and then forgot it after that. But this is the question that made me think, there's quite a lot going on here. It should probably have some revision notes. Let's go and write more revision notes. Too late to save me, because I'd already had a go at the question, but maybe it's in time to help you. Let's see. Right, sort of time travel, isn't it? I can't go back in time and make the question easier for myself, but I can try and go back in time and make it easier for you. What did I mention yesterday? Yeah, that was the parabola. Yeah. Same question both days. The answer is, surprisingly, just put the point in the middle of the x coordinates of the other 2, but the maths to it is more interesting. Right, what are we looking at? Okay, so it's a range of values. We have a triangle labelled with a variable x. There's a quadratic with minus x squared at the front. Great start. And we're asked for the complete set of values of x, for which there are two non-congruent triangles with these side lengths. So first reaction is, this is the side-side angle case, looking around that triangle, side-side angle. So it's ambiguous, right? And something I learned by thinking about this question is, nope, sometimes it's not ambiguous. Anyway, okay, what do we need then? I think that there are other various values of x. We will choose one eventually, I suppose. Oh, whoops, split screen, I think. So I think I want chat suggestions for how did you think about this question, or where do you start? What did you do? Maybe you know lots of rules about congruent triangles and you just wrote down some inequalities. Or maybe you drew a version of the picture and modified it a little bit to consider different cases where x takes different values. Maybe you tried special values of x. I mean, there's some ranges in the question. It seems like 1 to 5 is, roughly speaking, the total values of x under consideration. If I look at the different ranges. Sorry, I'll just show you the ranges quickly. None of those involve numbers smaller than 1. None of them involve values bigger than 5. So you could try some values if you like. And while chat's telling me what they're up to, okay. Matthew in chat, Callie's answered as well. I'll do the question in chat is, how do tutorials work if a college has no specific tutor for that course? And the answer is mostly they do, or they find someone. And there's a little bit of sharing sometimes where they'll find someone for a particular bit of the degree course to get someone else to do it. That's for first and second years. But by and large, the colleges who have math tutors cover the teaching for first and second year college tutorials. Pretty rare to get someone else. In some sense, if you're offering the maths degree and you've got math students, you should have a plan for how you're going to teach them the tutorial stuff. By third year, it's all very specialised, and we do things in the department instead with bigger groups of students across different colleges. But for first and second year, the colleges are pretty good at covering that. Good. Okay. Chat's not telling me how they started this question. I give them a half minute because they're probably typing quite long chat messages. Start musing about what I did, which is, I see a triangle like that with a 30-degree angle marked in it. I just found it very tempting to put a perpendicular in there so that I have a right angle and a length that I can actually find, right? Because I have that, it kind of looks like a hypotenuse to me. It's almost right angled as a triangle. It's not, but I can create a right angled triangle by drawing in the kind of height of this triangle, dropping a line down the middle. I will carry on by just doing that unless anybody stops me. I would prefer to do it the way that you did it if you've had a go at this question, but maybe no one has. Goodness me. Fair enough. I'm going to drop a perpendicular. So one approach you might use. Oh, here we go. Oh, yeah, okay. I'll wait. I'm not a very patient person. I don't know if you can tell that. Not in a sort of impatient, angry way, just in a enthusiastic, get on with it kind of way. Here we go. Right, maths. And I've now been patient enough to get EJ in chat. Can you feel the screen? Oh, if I press the correct button. Bottom left angle alpha and use the sine rule. Cool. Right, because, yeah, let's give that a go. I haven't this rabbit hole of perpendiculars and cosine rules and things. Let's do the sine rule, because we haven't talked about it yet. Okay, so here's a version of this where we're going to use EJ's method, and it's going to work, even though it's 5 to 7, and I haven't tried this before. Let's see what happens. So you're calling this alpha. And I was patient, and you typed the letter alpha. I don't know how you did that. Maybe you have a keyboard that has alpha on it. Goodness me. Right, okay. So sine rule, we haven't talked about it, but it says sine. So it says sine angle divided by the opposite length is the same for all 3 ways round that you might have that. sine alpha divided by minus x squared plus 6x minus 5. Alarm bells are going off in my head and probably in yours as well, because we only have two rules on this stream. One of them is please don't swear, and one of them is please don't divide by 0. The sign rule often encourages you to write down things where you have lengths, and the side lengths of your triangle should not be 0. So let's go, I hope x is not equal to 1. Question, I suppose. Greatest single number, there you go. I hope x is not 1. And over here, I suppose, when is this 0? When's this a problem? I should probably check because, well, it'd be a big problem, wouldn't it, if it was 0? I've already committed a crime. And it turns out that this factorizes quite nicely. And this is, from notes, sorry, this is x minus 1 times 5 minus x. I actually factorized that in 2 steps, right? I had x minus 5. I'm not some mad person with these. Let's do it properly. Okay. So I wrote out several things like this. Minus sign out the front because that's how I like to deal with these. X and x. Oh, it's not quite the one from before, but it's minus 3. No, minus 5. Minus 5 and minus 1. And then I brought the minus sign back in again. Well, anyway, this shows that it's 0. I hope x is not 5. The important thing. Okay. Made a mess of that. Yes, FA and chat. I should just read chat. There you go. You don't want x to be 5. Yeah, good. And Anonymous has come in to say that they just went through the conditions, right? We have these conditions. Alpha is an acute angle, so we're good. And the other two are just some stuff. They form inequalities, and then you're good. We're looking for 2 inequalities. The question's got 2 inequality signs in it. Good. The thing I'd like to know, Anonymous, is did you do that because you always do that on questions like this? Is that like your way of doing these things? Or did you do that because the revision notes have those inequalities in? Did you learn those inequalities in school, or did you learn them in the revision notes? Are we revising or not? Anyway, these both have x minus 1 in them. So I'm going to cancel that factor. If x is not 1, then I'm going to cancel that. And this now reads sine alpha over. I'm going to bring the minus sign in. It makes me feel more comfortable. Something that minus signs out the front in the denominator of a fraction just makes me feel, I don't know, it makes me feel nervous. So what have we got? Well, we've got several cases then. Sine 30, I've been avoiding converting it because I feel like I'm going to get it wrong, but here we are. It is crunch time. It is 1/2. I can put that in front as well. So various things going on here. Actually, so I suppose more than that, I hope that x is greater than 1, so this is a positive side length. Actually, I hope that x is less than 5, so that that's a positive side length as well. I want 1 negative, 1 positive, so that the signs work out. A picture of quadratic, 1, 5, roots, positive number in between, please. Yes, good. Did that come through? Yes, it did. Okay. So what do we want then? This is sine alpha. And the question asks us, we want 2 non-congruent triangles. We want ambiguity. We want confusion. And that comes when, well, quite often, when you get some value over here that's between 0 and 1. And if you can have that, then you will get an ambiguous case for sine alpha. I think that just works, doesn't it? No, because of the extra thing. How is it 1/2? Well, I multiplied, so that's 5 minus x in there. Bad handwriting. And this sine 30 degrees is just 1/2. Sorry, that's 5 minus x. Yeah, sorry, thanks everyone. Thanks, chat. I just try and multiply it by this factor. Okay, so we need this to be between. So this is ambiguous. For alpha, if 1/2 5 minus x is between 0 and 1. And if you do this, this turns into the inequality x being between 3 and 5. multiply by 2, subtract it from 5, yes. 3 less than x less than 5. So it gives you some ambiguity about alpha. It gives you two possibilities for alpha. But I'm afraid there is a bit of a trap. This is what I did. And I selected E, but this is sadly not the correct answer because of a second inequality that we haven't thought about. But this is officially called, I'm going to go a little bit long, I think, because it's 7 o'clock now and I'm not done. This is officially called sometimes the ambiguous case of the sine rule, but I think it's hard to think about this using the sine rule because of this problem that you there now stop, right? We've shown that to be ambiguous, it is necessary that this side, this is the A versus B sine alpha comparison. It's that term from a purple circle way up the board. It's necessary. It's not sufficient. There is an extra case, which is a little bit hard to think about, but it looks like this. In one of your cases, the angle alpha is far too large. We have this 30 degrees here, so we would like an ambiguity between two genuine triangles. So we must also check if we're doing it like this with the sine rule. Yeah, we could do the top triangle as well. Yes, EJ in chat back again. We could think about this angle as well. And if you do that, you find that in one of these cases, that angle is negative. I guess that's going to be hard to spot, but no, you'll spot it. Yeah, you'll be okay. The sine rule, you don't know the length of this side. That's going to be tricky. But if you could somehow follow through, you'd find that in one of the cases, that angle is negative. Because we haven't written this down. We're definitely not going to take arc sine of this expression because I don't know what it is. But in one of these cases, alpha is too large. It's larger than 150 degrees. Question, how on earth do I know that? I'll put this thing over here. Depending on the value of x. So sometimes the thing I just said. How do I know that that's sometimes a problem? And answer, I didn't think of this until too late. I looked at the answers, but yeah, there's something I haven't thought of. Dr. Prokop in chat says the two triangle ambiguous case requires, and then they state the inequalities. And in particular, one of the requirements is that this side is supposed to be actually shorter than that side. If they swap over, then in one of your cases, the triangle that you're describing with the sine rule is this one. Nobody is going to like this picture. This picture is going to be absolutely awful. 30 degrees minus large number, so negative angle, negative, I don't know, 10, 20 degrees or something, and then an angle over here, which is, oh my goodness, 170 degrees. And that is terrible. Most people don't even believe in negative angles, right? So it's sort of surprising perhaps that your sine rule can discover things like this which are not a triangle, but this is what the problem really is. That is coming out of this sometimes. Here's when it happens. And if you love the sine rule and you want to do the sine rule, you don't have to stop with the sine rule. You don't have to give up. Here's how it happens. So picture of sine between 0 and 180 degrees. Maybe I'll call it pi for radians, just for value. Here's a picture of sine. We would like two values for sine alpha, which we generally get. We've got this value of half 5 minus x. Okay, so we generally get 2. Now the thing I'm worried about is that this large angle over here will be too large. What do I mean by too large? Well, too large concern. And that concern is if alpha plus 30 is even larger than 180 degrees already. Oh, I'm using degrees again. I can't use pi over here. The question's already in degrees. Now, if this is the case, then so it's maybe turning things around a little bit, but 30 degrees will be larger than 180 degrees minus alpha, so this can be a problem if alpha is an obtuse angle that's very big, so bigger than 150. Then over here, this distance between 180 and alpha, it'll be very close over here, bigger than 150, so close that this will be so low, if I select this, so low down because this 180 minus alpha is so close over here. So too close to the sun, too close to 180 degrees, angles are too large overall. What's the critical point? The critical point is if this 180 minus alpha is 30, which is a lovely angle. If that's 30, and this is 150, and you know the value of sine of 150, so the critical value, the point where it all goes wrong, is over here, at sine of 30 degrees. So this is a long-winded argument to say, essentially, A less than B, or is it A greater than B? There's A less than B, which is one of the inequalities. You need these signs to work out down the end. Not sure I've done a great job of that, but the punchline down here is that also need for triangle to actually exist, both of them, you need this value, sine alpha, you need that to be greater than sine of 30 degrees. So that you know that the angle that you're getting for the obtuse case is smaller than 150 degrees. Another case with a decreasing function, look, decreasing over here, where I need this value of sine to be large so that the angle is small. Talking about obtuse and acute separately, all very complicated. That's not too bad, that just says that x is less than 4. Yes. So this extra bit, I find that really hard to think about. I don't know if you could tell. I didn't do a great job of explaining it, sorry. There's a better version written up in the solutions to the revision problems, where one of the revision questions that we didn't talk about, number 13, is that discussion with the picture of sine. I think I did a better job over there. What am I saying? That discussion being quite complicated is why I've decided in the revision notes to talk about the cosine rule instead. But maybe that's just me. Right, we're still here. Oh no, okay. Some people are still here. Hello. Sorry, I realised that I've just overrun massively and I'm just rambling about sine of different angles. I don't know. I find it easier to think about this by drawing a line in and going, okay, if this is a real triangle, then you've got to have this length here has got to actually exist, and the other one will come from the side length x minus 1. Instead of being off that way, will surprisingly be off this way to get this triangle on the right. You've got this like isosceles triangle you can draw. The ambiguous case is always about having this isosceles triangle. What does chat say? Yeah, so it requires some inequalities. Or as I like to think of it, this perpendicular height has to actually be larger than the other side length, so you get this ambiguity, but not so much that this long side is actually too long and it flips back over here somewhere when you reflect it over the dashed line. Right, okay, I think I'm getting a bit too tired to say sensible things about TMUA questions, so I think I'm going to wrap up very soon. Anything else from chat? I'm going to state the parabola question, I think, because there was a request, and it feels complete to have it in here at the end of the video, but let's go. So let's go, So I've been showing everyone who comes to the open days at the maths department this question with y equals x squared as a parabola. A and C are fixed points on the parabola, with B somewhere in between. I would like to maximize the area of the triangle ABC to maximize the area of triangle ABC. and I would like to know, where should I put B? And if you want the answer, we've said it earlier in the video, probably you should try and work out what's going on. I love this interview question because I can ask people what they're thinking. I can do follow-ups and check their understanding. Sometimes people have this really good idea that I can delve into, like, where's that come from? How does that idea work? Why do you want to put B there? And then if I don't like their explanation, I can ask them for more explanation. If they get through and we get a good convincing answer, then I can change the function to ask a kind of similar question with a different function. I can change what we're asking about over here. So I really enjoyed using this, but I retired this interview question. I retired this interview question. I just called it at the end. Thank you, Callie, for doing a great job on the writing stream. Yes, I agree with you. Right, yes. Okay, right. Eddie says I've cut out already. Microphone's gone. I think I'm still going, but I'm going to go there. Could I explain the question? Pause the video or leave if you don't want to see the answer. Here comes the answer in 5, 4, 3, 2, 1. I think the best formula for the area of a triangle for this question is to call this the base, because it's fixed, and to think about the kind of perpendicular height to B. We'd like to maximize that. We'd like to make that as large as possible. So a really silly thing to do would be to put B over here somewhere, where I'm going to draw in a little parallel line so that you can see how like not tall that triangle would be. Be not good. And over here, where that parallel line crosses over here, is sort of like equally bad. Equally bad because it's the same height, right? Parallel lines. It's the same base, same height. Doesn't really matter where you are on the parabola. The only thing that matters is where you are on, I suppose, some parallel line. No, sorry, which parallel line you're on. Where you are doesn't matter, right? They all have the same area. Any triangle from this. So sort of fun fact, I don't know. Like you can sort of maybe try and trick a GCSE student like this, right? You have parallel lines, and you choose 2 points down here, and you can put this one anywhere. Anywhere, but these are fixed. Where should you put B to maximize the area? And people will probably say, well, you know, put it in the middle, right? Because that feels like it should maximize the area. But the correct answer is it actually doesn't matter. These all have the same base and the same height. So you can put it wherever you like. That's not the right answer for this parabola, of course, because we have the freedom to do a different line. A different parallel line will give us a larger triangle. Here's another one. I'm doing a kind of height chart. It's an angle, but like a height chart, like if you're in a sports hall demonstrating your jump height or something, you get these height charts. These triangles are taller. And what's happening to these points for B? They're moving closer together. Where does this process stop? If I push it too far, then there are no points. Over here, there are 2 points. Definitely the interesting maximal case is where you get exactly 1 point, which is when the tangent is parallel to AC. And now we've got some algebra to do. To have the tangent parallel to AC, we want, let's write it out, gradient of that, excuse me. We want the gradient to match the gradient at B. I'm using lowercase letters for the x coordinates. This simplifies really nicely. So the answer just turns out to be, put it in the middle, A plus C over 2. Hooray! Right, good. Okay, I'm going to call it there, I think. Such good fun. And if you do that, we talk about like other cases, other functions, like we hardly have to do any calculus here because we kind of know derivatives should match up, which is a bit like doing calculus, I suppose, to find that derivative in there, but no. It could be much worse. We could have written down a formula for the area for the triangle, but having the correct formula for the area of the triangle means, you know, this is fixed, this is fixed. This is the interesting thing, H. Good, right, okay. We've got surprisingly many people in GCSEs in chat, but yes, nice, good. Okay, right, we're going to be back in about 166 hours for another maths admissions test live stream where I don't have any open days next week, so I think I'm going to be more awake Also, next week is logarithms, which is, I think, one of my favourite topics that's on A-level mathematics. So I'm really looking forward to doing some of those with you next time. I think the show is more fun for you if you've had a look at the questions in advance and they've been published on the page. So if you want to see some logarithms, GCSE students, you're definitely not going to learn any logarithms at GCSE, but if you would like to find out what they are, you can have a look at the revision page if you want to get a sneak preview of some A-level maths. Right, anyway, thanks for joining in chat. Thank you for the voting. We'll be back in 166 hours, more or less, for another episode of the Oxford MAT Livestream Livestream. Until then, have a nice evening, have a nice weekend, have a nice week. I cannot talk. Those are the only words I will say. Yeah, similar method, similar idea, but I can probably build a function. Yeah. I'm done. Right, good. See you next week, everyone. Have a nice evening. Bye.